So what's going to be really useful for this lecture is if we know how to add two sinusoidal waves together. And we have a method for doing that, and it's called phasors. So let's talk more about how to add two waves together using phasors. Now, the thing I really like about phasors is that it is a graphical representation of how we can add multiple waves together. So consider adding two waves together. We might have E1 and E2. Now, E1 might have an equation of E1 equals E naught sine omega t, and E2 might be exactly the same but just have a phase difference. So it will be E2 equals E naught sine omega t plus phi. So the way that we can represent these waves graphically is by drawing them using vectors. So phasors is basically a method of adding waves via vector addition. So we'll draw, for example, the vector representing the sine wave for E1. And we would draw that as a vector that makes an angle of omega t with the horizontal axis, and it has a magnitude of E naught. So its projection onto the vertical axis is going to have a magnitude of E1. The second sinusoidal wave, E2, remember its equation is E2 equals E naught sine omega t plus phi. It's going to have the same magnitude. It's going to be E naught as well, but it's going to have an angle with the horizontal axis that is an angle phi greater more than omega t. So remember, it's omega t plus phi. So we've just shifted it around from the horizontal axis a little bit more. And its projection onto the vertical axis is going to be E2. Now, remember with vector addition, we add vectors head to tail. So we have our first vector, which is our E1 vector. So remember, it has a projection onto the vertical axis of E1, and it is E naught sine omega t. And then we have another vector. We add our E2 vector onto the end of that. So therefore, our total vector, we join the two ends together and we end up with a total vector, and we'll call that vector, for example, E. Now, the projection of E onto the vertical axis, you can see, is going to be the addition of E1 and E2. So when we add these two vectors together, we have our resultant vector E, and now the resultant vector E is going to make an angle with our initial E1 vector, and we're going to call that angle beta. I'm just going to interrupt myself for a second here because I need to tell you something first before we move on so the next bit makes sense. So what we're doing is we're essentially adding two vectors. You can think of those vectors as being the sides on this triangle B and C. Now, our resultant vector is going to be this vector A here. Now, I'm going to show you a shortcut that basically uses the cosine rule. Now, the cosine rule is, for example, if we wanted to relate the angle A to the side A, the cosine rule says that for a triangle like this, we can say A squared equals B squared plus C squared minus 2BC times cos A. And that works for any angle that we have here. The reason this is important is because for the angles that we're going to be looking at, we want to know what the angle is between the first vector that we write, which is the first vector that we add, which is going to be the side B, compared to our resultant vector here. So we are going to want to find the angle C. And what we do is we call that angle beta in what I'm about to show you. So we need cos C to sit here. So therefore, we are going to say that something like C squared equals A squared plus B squared minus 2AB cos C. So for our equations, this is going to equal E naught and this is going to equal E naught. These are going to be the same thing. Now, they don't necessarily have to be, and you can use this form of the equation even if they're not the same thing, okay? But for the purposes of what I'm about to show you, they are going to be the same thing. So what we're going to say is we eventually want to work out what A is. Now, A is going to be E1 plus E2, because remember, this is going to be our E1 vector, that's going to be E2. Okay, so C squared is going to be E naught squared, because even though this is E2, it has a length of E naught, so it's going to be E naught squared, equals, now A squared is going to be E1 plus E2 squared. We don't know what that is, but that's what we're trying to work out. Plus E naught squared, now this is our B squared, remember it has a magnitude of E naught, minus 2 times E naught, which is our B, and then times A, which is our E1 plus E2, cos, now remember I said this was going to be the angle beta. So therefore, let's actually simplify this. So we can cancel our E naught squareds, and then we'll move this completely over to the other side, and I'm just going to flip it around. So what I'm going to say is E1 plus E2 squared equals 2 E naught E1 plus E2 cos beta. Now, this cancels with this, therefore our resultant E1 plus E2 is equal to 2 E naught cos beta, and that's going to become really useful to know. So let's go back to the main video. So for simplicity's sake, let's analyze this vector addition at time t equals 0. So when we do that, we end up with our resultant vector E is going to equal 2E naught cos beta. But what is cos beta? Well, you can see our angle phi here. Now phi is given to us by this middle angle, which is going to be 180 degrees minus phi. And that middle angle is also 180 degrees minus 2 beta, because remember, we have a triangle there and all the angles in a triangle add up to 180 degrees. And when we equate those two, what we end up with is beta equals a half phi. So therefore, at time t equals 0, we're going to have 2E naught cos a half phi. And the reason that that's useful is because we want everything in terms of the phase difference between the two waves. We don't want it in terms of, well, what is the angle between the first vector and the resultant vector. And this is going to become more obvious when we add multiple waves together. So the projection of E along the vertical axis at any time t is going to be given to us by the following equation. Now, our projection we will say is E subscript P, and that's going to equal E sine omega t plus a half phi, which is also equal to 2E naught cos a half phi sine omega t plus a half phi. So what we can get from this equation is that we have some projection, EP, and it has a magnitude that is given to us by 2E naught cos phi divided by 2. And so our sine omega t plus phi divided by 2, that's our changing orientation, but the magnitude is given to us by this 2E naught cos phi divided by 2. So let's have a look at a few examples. So let's have a look firstly at our extremes. When is our resultant going to be a maximum and when is our resultant going to be 0? So this is going to be our constructive interference and our destructive interference. So the maximum is going to occur when cos phi divided by 2 equals 1. And this is going to happen at phase differences or phi's of phi equals 0, 2 pi, and 4 pi. 6 pi, etc. So these are our multiples of our wavelength, remember? So this all makes sense. When we have constructive interference, we expect a phase difference between the two waves of multiples of the wavelength, and this is exactly what we see happening at 0, 2 pi, 4 pi, etc. The resultant is going to have an amplitude of 0 when cos phi divided by 2 equals 0. And this is going to occur when we have phase differences phi of pi, 3 pi, 5 pi, etc. Now pi, 3 pi, etc. This is all multiples of half wavelength. So remember, when we have a half wavelength shift, we get destructive interference. And this all makes sense with what we know from previously. So let's have a look at a couple of examples. So when our phase difference phi is 0, we should expect a path length difference that is also 0. So therefore, this should be when we see a maximum in our resultant vector amplitude. And that is what we see. So we add two vectors of E naught with no phase difference, and our resultant vector amplitude is going to be therefore 2E naught. When we have one vector that is 45 degrees different to the other one, we can see we have a phi phase difference therefore of pi on 4, and we have a path length difference of lambda divided by 8. And our resultant vector is going to have an amplitude of 1.85 E naught. So therefore you can go through and have a look at the rest of them. But for example, another one that we'll point out really quickly is what happens when we have a phase difference of 180 degrees or pi. Remember, this means our path length difference is going to be lambda divided by 2. So we would expect destructive interference. And that's exactly what we see. Our amplitude of our resultant vector is going to be 0. And skipping straight back then to the last example, this is what happens when we have a path length difference equal to 1 wavelength. Our phase difference is therefore going to be 2 pi, and when we add these two vectors together, we see that the resultant vector has an amplitude of 2E naught. And that's how we add two waves together via the phasor method.